In this class, we are going to use all the concepts and physical quantities that we have used in the two previous presentations corresponding to the module of point dynamics. And we are going to focus on the physical magnitude of the quantity of motion or linear momentum already introduced by Newton for the study. What we are going to do is to see the importance of using this magnitude of the quantity of motion. A new magnitude will also appear, the mechanical momentum, and we will enunciate another principle that we need to evaluate very well the problems in classical dynamics, which is the principle of conservation of the quantity of motion. If we look at the evolution that appears here of Jota, we see that when the skateboard meets the brick, what occurs is an impact, and Jota tries to maintain its condition of motion. However, he tries to continue with the same state of motion that he had at the beginning, as we enunciated in the law of inertia. But of course, he meets on his way with a wall, and the surprise is a little unpleasant for Jota. But we are going to analyze the fact. We are going to reflect on what would happen if Jota would be thrown off his skateboard at this point. Let's imagine that Jota's body simply hits the wall at a speed of 5 meters per second. We could imagine what would happen if instead of Jota going on the skateboard and being ejected simply with his body, with his mass, he were on a tractor with the same speed with which he had 5 meters per second, he would impact on the same wall. Let's see what would happen. Something that would seem logical. We had left poor Jota in this situation, but what would happen if he were on a tractor? Well, what would happen is that in this case, Jota would not suffer any damage. What would happen is that we would destroy the wall, but the speed we have said was the same. The speed we have said was 5 meters per second. What is the difference? Well, this is the reason why Newton began to introduce the concept of the quantity of motion, a linear momentum, also known, and that will appear in the bibliography. The linear momentum takes into account not only the velocity of the body at each point, not only the kinematic characteristic of the velocity at a first instant. In this evolution of the basketball, at a first instant we can say that its velocity is v sub 1, and at a later instant v sub 2. But to have a better knowledge, a better dynamic study of the movement, it is very important to accompany this kinematic magnitude, the velocity of the mass of the body, and that is just what defines the concept of the quantity of movement. The quantity of motion is a vector defined also by the scalar magnitude of the mass of the body and by the vector magnitude of the velocity. Will therefore have the same direction and sense, as the kinematic magnitude of the velocity and its modulus will be multiplied by the mass of the body. In the international system of units, it will therefore have units of mass, kilograms, and units of velocity, meter per second. If we analyze how the quantity of motion of this ball varies along this trajectory, we have in the first instant the initial quantity of motion p sub 1, that would be given by the mass of the body and its velocity at that instant and at a later instant. With the velocity v sub 2, the quantity of motion would be the same mass of the body. It does not have to vary as long as they do not tell us otherwise, m times that velocity v sub 2. If we make the difference to see how the amount of motion varies as a function of velocity, we would have that p sub 2 minus p sub 1 that would define the variation of the amount of motion would be equal to the mass times v sub 2 minus the mass times v sub 1. That is the mass times the variation of the velocity. This allows me to define the variation of the quantity of motion. If I now wish to analyze how for small time intervals the amount of motion varies as the motion of a body evolves, what I will do is to consider very small time intervals and work with the differential of the amount of motion with the variation of the amount of motion with respect to time. What will that give me? This will define the mass by the variation of the velocity with respect to time, but this magnitude or this derivative is well known to all of us. This is defining the kinematic magnitude acceleration of the body. What have we arrived at? That the variation of the quantity of motion with respect to time is defined by the mass of the body and by the acceleration. But mass times acceleration of the body we have just seen in the previous class that it is directly defining for me. Newton's second law. The force is defined by mass and acceleration. Then we have a new statement for the fundamental principle of dynamics or Newton's second law. The force or the resultant of forces that are acting on our system is also going to be defined by the variation of its quantity of motion as a function of time. Let's see what happens now to see these forces. If we have to take into account all types of forces that are acting on our body or on our system, or only a certain type of forces, we are going to analyze a very simple system, a system composed only of two particles, the yellow particle and the green particle. We have a yellow particle of mass m sub 1 on which two forces are acting, an external force F sub 1 and a force due to the other mass, the force acting on 1 due to 2, and on the green mass of mass m sub 2 will be acting also an external force which we consider represented by this vector F sub 2, and the force due to the interaction of the mass m sub 1, F on 2 due to 1. In this case, if we analyze now the variation of the quantity of motion for particle 1 and for particle 2, what we have is that the variation of the quantity of motion for 1 will be due to the external force F sub 1 and to the interaction force between the two particles F on 1 due to 2, and for the second particle, its variation of the quantity of motion would be the external force F sub 2, and F on 2 is acting due to 1. But in addition, since I have the interaction of two bodies, I know that the principle of action and reaction, Newton's third law, is going to be fulfilled. This law tells me that the force that is acting on 1 due to 2 is going to be equal to minus the force that is acting on 2 due to 1. What happens? If now what I do is to take into account these two expressions with Newton's third law and add the first and second terms, I get from the sum of the first two terms, I get this here. And from the sum of the two seconds, these second terms will cancel out, because one is equal to the other in modulus and direction, but opposite directions. So I am left with only this contribution. What we are saying is that the variation of the quantity of motion of a system depends only on the external forces of the system and not on the internal ones. The only forces, therefore, that are capable of varying the state of motion of the system as a whole is due to the external forces and not the internal ones, because they are going to be compensated 2 by 2. We have, therefore, that from this new formulation we can already speak of Newton's second law as the forces that are acting on a body, on a mass. I can analyze it from the mass of the body and the acceleration it carries, or that its variation of the amount of movement is determined by these applied external forces. What happens now if what I want is to know in function of the force the variation of the quantity of movement that is taking place? Well, from this expression I can put that the variation of the quantity of movement is defined by the force and the time variation that I want to consider. If I integrate this expression, I get this expression here. What is this expression telling me? That the variation of the quantity of motion is defined by this integral between the time interval of study that I am choosing. It is telling me that I am going to get the same variation of quantity of motion by two different paths. A first path can be that a very large force is acting in a very small time interval, and another path may be that a small force is acting but during a large time interval. In both cases, the variation of the quantity of motion will be the same. This magnitude that has appeared from this integral is the one that is defined as the mechanical impulse, and that we are going to use a lot, and it is used a lot in impacts in collisions. The units, if we look at it, what are going to be the units of this mechanical impulse? The units are going to be the same as those of the quantity of motion, and we can also represent it as newtons per time unit. Let's analyze now what is going to happen if I have a system where I will always be able to apply the relation that I already have between the variation of the quantity of motion of my system, as we have done before with the two single particles, equal to the resultant of the applied external forces. But now we consider the case where the resultant of the applied external forces is null. If it is 0, what is going to happen? Well, if it is null, what will happen is that this term is 0. And if this term is 0, we are saying that there is no variation of the quantity of motion. If there is no variation of the quantity of motion, is the same as saying that the quantity of motion is constant. Let's apply it to a very common and very practical case, which is the study of collisions or percussions. Let's consider two bodies resting on a very smooth surface in which we will not consider friction forces. Therefore, there are no external forces, only the forces that will act are those of interaction between the two bodies, mass 1 on mass 2, mass 2 on mass 1. And initially what we will consider is that mass 1 is subjected to a motion at a translational velocity to the right, represented by the velocity vector v sub 1, and mass 2 velocity vector to the left v sub 2. In the vertical direction, the forces give us a zero component. The normal on 1 equal to the weight of 1. The normal on 2 equal to the weight of 2. At the moment of impact, we have the equivalent of the principle of action and reaction. Newton's third law, the force on 1 due to 2 and the force on 2 due to 1. And in the end, what is going to happen is that due to that internal interaction, I am going to have some final velocities represented by these asterisks for body 1 and for body 2. If we apply this law that relates me to the quantity of motion with the external forces now are not acting if they are not acting. And the total amount of motion of my system is going to be constant. I can say that the amount of motion before the impact will be equal to the amount of motion after the impact. The amount of motion of particle 1 plus particle 2 equals the final amount of motion of the particle 1 plus the final amount of motion of particle 2. That is, I get this equality. This equality, which is a vector equation, times the representation of the magnitudes that are involved, is giving me the relationship between the velocities before the impact and after the impact of the bodies that are interacting, and is of a very broad application in many phenomena that we will be addressing in subsequent classes. We have therefore made an analysis of two concepts also very important in dynamics, which is the physical magnitude of the quantity of motion linear momentum, and what is the principle of conservation of the quantity of motion. We can already analyze it for particles, and we can also apply it to particle systems, and we will see it in the following classes of a great application.